Hi, Marcos. Good afternoon.
Hello, good afternoon for you.
And good morning, good afternoon, and thank you for connecting to everybody today to this webinar. Um, Today we are going to talk about a topic that I think is very interesting for different kinds of positions, not only electrical engineers that are in all the time in the lab or designing. And I wanted to ask you, Marcus, before starting, is the time one of the key challenges for an electrical engineer when there is an important project?
Yeah, most of the time, yes, it's a very important parameter because typically we underestimate the time that we need to do the things. And okay, it's nice to well, it takes for me 1 month to do a design, then 2 months to test it and so on. But we underestimate the problems, the issues that we can find during the testing or maybe during the design phase, and also things like are not related with our work. Maybe you're gonna be sick or something like that. So yeah, time is very critical, and there are a lot of customers that come to us in order to, well, I need this inductor, this transformer for yesterday.
Yeah, that's not possible. And sometimes the only thing I can imagine in specific things that can affect the performance of the converter. But you have said it's not only the specs you find in the lab or when you have to test the sample. There are also more things that sometimes you can predict in the future. So that's why it's important to be in time and to be sure you come with the appropriate tools for these projects.
Yeah.
So okay, we can start. I'm going to explain the introduction. Um, the two tools you are going to use today. Maybe you are going to focus more on the Frenetic magnetic simulator, but it's good just in case you're going to see a little bit of Frenetic AI. I'm not sure, maybe not, but I think it's important to put in context that we have two different tools that can help to save time and to be precise in the workflow you have day by day. So the first one is Frenetic AI. It's designed for the converter design. You can do some calculations. You can download the LTSpice files, and you can also see all the specs you need before going to the Frenetic magnetic simulator. This is for customize your magnetic, and it's based on different data and scientific models. So I think, Marcus, today you are going to use more Frenetic magnetic simulator, maybe?
Yes, more focusing on Frenetic Simulator than in Frenetic AI.
Okay, so let's start.
Okay, thank you, Ellie. Okay, so welcome to this webinar. Today, I would like to tell you to everyone a story of an engineer that works for a tier one company. This story, it's something that probably you get some familiarity because this story start a Tuesday. It doesn't matter the week. Your boss comes to the desk and asks you if you can test a board that arrives yesterday. The board is a back converter, 3 kilowatts. You have everything in your laboratory. You have the power supply, you have the load, you have the oscilloscope to check any waveform in the system, but there is only one missing component, which is the inductor. So your boss asked you if you can have the result from Thursday, because the deadline that we are in a hurry, it's delivery this sample, this prototype to the customer on Friday. So this is the outline, or the, let's say, the schedule of our friend, okay? So we can start thinking that our friend doesn't have any knowledge about magnetics, just the base. So he spent the first 2 days doing the classic approach, or the manual approach, which basically is looking into internet, reading some papers, and then designing an inductor by scratch with the material that he has in the laboratory. But then the third day, in the morning, the reality hits him. He tests the board and things happen. He has just one day left, and he needs to search for another options. And finally, he becomes with a plan, the plan which is Frenetic. So let's come back to the first day. Our engineer needs to design an inductor for a 3 kilowatts buck converter with this input specs. So the first thing that this engineer do is calculate the necessary inductance for the converter. Okay, he assuming that probably with a ripple around 30-40%, it's fine. So he used 40%, calculate the duty cycle, and with the switching frequency, he gets around 50 microhenries. Then he go to the laboratory and then starting to gather some material, okay, from the lab. He has some cores, some wires. He read before that probably he needs a gap in the core. He doesn't know exactly, but he pick up like E55 with 3 millimeters gap, PQ5050, and also round wire, one leads wire, and another leads wire, but he has only 3 meters of the wire, so it's very small quantity, so he needs to be careful about that, okay, depending of the design. Then our friend starting some manual calculations, okay, so he goes to the web, starting to read some papers, and then apply some process and equations to do the calculations. For the core, he takes one of the options that he has in the laboratory and start to calculate the inductance regarding the AL value, the B peak to see if it's above or below saturation, the BAC regarding the ripple to get the core losses. And for the core losses, he found some equations, statement equations in this case, with some coefficients that the supplier are giving in the web. So he applies the formula and calculates some values. For the winding, he followed the same process. So he find that he needs probably a current density between 5 and 6, okay, to be fine in the temperature. He started a calculation with the round wire, and he realized that with round wire, RDC it's very fine. It's very small. But then there is another losses that needs to be considered here, which are the RAC losses, or the AC losses, sorry. So he found a approach which is made by Dowell in the past, okay, with some equations that depend on the distribution of the layers and also the wire diameter that you have. You have an amount of losses, or a resistance which is called AC resistance, that produce an extra losses. So we not only to be considered the conductive losses, we also need to consider these AC losses that are produced by the skin effect and the proximity effect. There are another phenomena or another losses that our engineer for the moment is not considering because he doesn't know. He need to do something quick. So he just spent one day doing calculations in his notebook. So the first design that he did doesn't meet the requirements. So he need to think about that on the day two. So what he do is just go into Excel, implement all the formulas that he learned yesterday, and then he has like a kind of automate process. So he can iterate between different cores, different windings, and finally, by the end of the day, he get this solution, which is the using the A5055. He choose this core because it's the bigger core that he has and is gapped. He calculate the number of turns, inductance, the maximum B field. So he realized that he's below saturation, and he used the leads wire, the 40 strands and 0.2 strand diameter, because with the round wire, AC losses become crazy. And he used 3 layers and 3 parallels to keep the current density below 6 amps per millimeter square. And he get these values, which in principle in paper, he doesn't know exactly which is the temperature of the design. But, well, you have less than 1 watt in the core. There are some forums that our friend check in order to see which is the thermal resistance of the ferrite, and 1 watt should be fine. It's not a problem. And also regarding the winding, he calculates 4 watts. 4 watts with this amount of copper, yeah, maybe we should be fine, okay? He still doesn't know the temperature, but he has way to control the temperature. So then he has everything ready by the end of the day too. So he has 1 day just for testing the board, testing the inductor, and get all the results and send to his boss. And then the day 3 in the morning, the reality hits him. What happened here? He put the inductor, he built the inductor in the laboratory, he placed it in the board and start to run a test. He see that the board is fine. The board works perfect. The waveforms are clean, the system delivery, the full power, the output voltage is correct, the output current is correct, but something happened. Something is starting to smell. Yeah, it's the coil former and also the tape of the inductor, which is starting to smell like melting. So he put a FLIR camera and he realized that the winding becomes very hot, okay? And it's something that it never stopped. So he entered in at what we call it a thermal runaway. When you have the temperature increasing the losses of the magnetic, and then these extra losses generate an extra heat. And finally, he doesn't stop the test. And finally, the inductor, the core, reaches the Curie temperature. So the core loses the magnetic properties. And, well, if you lose the magnetic properties, you only have just a copper with some resistance. So basically what you have is a short circuit. So the semiconductor, the MOSFET that he placed or that he has in the board blow up. Well, he will be very desperate at this moment because he doesn't know what need to do. He has another prototype. He can run another test, okay? Because he doesn't have time to repair the board. But he need to, let's say, have a component that at least can run during 2-3 hours, okay? So he start to think about different options. Maybe I can use FEM. Yeah, we can use a finite element analysis program, but maybe this is not a good idea because, well, if it was in the day 1, probably I have time to get a solution, but I need something in 2-3 hours because I need also to run the test. So he goes to his break, take coffee, and he's starting to talk with his colleague and mention the problem. You know, sometimes engineers just talking with the colleagues and the colleagues then give an idea and it's like, whoa, we see the sky. So in this case, the colleagues say, why don't you use Frenetic? Frenetic? Yes, we bought a license 2 weeks ago. It's pretty fine. You can maybe design an inductor in just a minute. Well, I can try. So that's the plan, which is using Frenetic. So let me go through the tool to show you how our friend do the process. He select an inductor and go to the back topology. Very easy, right? So then the first thing that he see is the waveform tab. Okay, here I need to write some specs. Easy, right? I have everything. The switching frequency, the input voltage, the output current, converter output power. Oh, I need to write here a temperature, the ambient temperature, probably. Well, the board is inside an enclosure, and I measure this temperature, and it's something around 60. It's not 25. Okay, I have here a wavefroms. Yeah, it looks like similar to the ones that I measure with my oscilloscope. Well, what are the next steps? Okay, maybe I can check first the design that I did. So he goes to the core tab and select first the material. Okay, it's from TDK, N87, and the core is an E55, right? Yes. Okay, so I have the number of turns calculated, 14. Ah, I have also a gap, 3 millimeters gap in the center leg. Okay, if I apply, or maybe, oh, yes, I need to click on calculate. So he saw this, okay, 51, it's matched with the value that I calculate in my notebook. Okay, if I run the core, well, I have here the B peak, I have here the BPKC, and that's pretty much aligned the values that our friend calculated previously, okay? The core losses, maybe it was a bit higher, but well, for the moment, it doesn't matter because the core losses are very small, okay? Just for your knowledge, our engineer used statement coefficients based on sinusoidal excitation. And here we don't have a sinusoidal excitation. We have a square excitation. So you need to do the right calculations here. But the core is fine. And this is not the problem. He also see in the thermal camera that the core is not the problem. It's not very hot. So he goes to the winding and then, okay, I need to put my leads wire. Well, in the wire type, yes, leads, of course. Well, parallels, I have three layers. Number of insulation layer, I don't know exactly, so I can keep like 0. Strand diameter, well, I know, it's 0.2. And the number of strand is 40. And serving, what is that? Well, let's put single servet. Oh, maybe it's referring to the silk of the leads. It had sense. Yeah. So, well, if I click on run, okay. Well, that's not the 5 watts that I calculated by hand. And the temperature also, it's a bit high, okay? So, well, I have a problem. Oh, proximity losses, 7 watts. Whoa, that's too much. DC losses are pretty aligned with what I calculated more. Oh, yeah, because this one, it's related to the temperature. I see. Yes, it has sense. But the proximity losses, why are 7 watts? I don't know. Well, maybe if I try the other wire, it needs to be better because I read that proximity effect, skin effect are related with the strand diameter. So I can put the other wire that I found in the laboratory. Oh, really? Yes, the losses are less than I expected. It should be fine, but oh, I have a problem. I need 5 meters of wire length, and I don't have 5 meters. I have 3 meters. Maybe if we reduce one parallel, even if the current density is higher, we can do something. Well, we are even more than 3 meters, just by a small value. But maybe if I reduce another parallel, well, yeah, I have enough wire that losses are higher because the current density and the DC losses are very high, okay? So this doesn't work. Well, yeah, probably if I use instead the A55, the PQ50, I can fit the wire with a small space because the PQ has a round pole. So the round pole, in principle, needs to have less or needs to or require less wire meter. So let's do with the PQ55, 50, sorry. Okay, I can keep the same turns, but I remember that this PQ5050, it has 3 gaps of 0.6. So I can check if everything is fine. Well, it's fine. We are even below the saturation. The PPKC is higher, so the core losses are higher. But oh, wait. It's not N87. It's N95. Oh, that's also more nice than previously. Okay, so the losses here are below, but you know, reduce for 1 watt to 0.3 doesn't solve the problem. So he go to the winding, and the first thing that he sees to check the other wire, because he has a lot of meters in the spoon. So he put again the 40 and 0.2, 3 parallels, 3 layers, and he thinks that maybe with less length he has less losses. Whoa, what happened here? I have less losses, I have less length, but proximity effect are not as the previous one. Why? The Windows is the same. So our engineer, our friend, he doesn't know right now, but he is reducing the fringing losses. The fringing losses that we are not considering in the manual calculations. And of course, there are ways to give this approach. There are ways to calculate the fringing losses. But as he doesn't has any time, he just doing the easy thing, which is going to the inductor design, but very simple designs. So he realized that, well, with this solution, it works. It can be done. But as he has time and he just doing a couple of simulations, he also tried the other wire, okay? So he put the 0.71, the strand diameters, and then he reduced the 2 parallels and 2 layers in order to have less than 3 meters. And yes, he has, it's in the limit, but he has less than 3 meters, and he get even less losses than previously. So finally, he has his solution. So he quickly ran to the laboratory, built the PQ5050 with this wire, test the board, and he can run tests during 2-3 hours until he get the steady state temperature, 100 degrees, a bit more than what we predict, but it's fine. And yes, he go to the desk, to his boss desk to give the good news. Okay, so yeah, we can send the board tomorrow. So basically, the message here is, well, sorry, don't let traditional methods slow you down. I mean, I don't want to say that traditional methods are bad. In fact, that's very nice. If you don't have nothing, I mean, if you need to do some calculations, and even for the core perspective, it was fine. yes, we need to adjust maybe the statement coefficients to the proper excitation. And for the winding, dowel is also fine, but dowel doesn't take into account effects like the fringing flux or the effects that you need to calculate at the end, the resistance for a fixed temperature. And these losses can create more temperature. So at the end, you are in a loop and you need to find the steady state temperature. So it's very difficult to do this one manually. You can do, but you need time. And if time is important for you, use Frenetic magnetic simulator. You can design, validate, and optimize in minutes, not days. And that's all for the webinar. And I would like to add something, which is this story is not a real story, okay? So it's a story that I designed and invented. But as just an anecdote, if you see this picture here, okay, this is a real calculation of that I did for the inductor, okay. And when I prepared in the webinar, because I'm not very familiar with the Dowell equation and the manual approach, because I typically use Frenetic, it takes for me a lot of time to do the calculations. It's like one day and a half doing calculations, and I have everything here in my notebook, okay? So the story finally becomes real. Okay, in this case, my deadline is not sending a board, it's have the material to do the webinar, okay? So I spent like 1 day, 2 days only doing manual calculation. And in Frenetic Simulator, I can do the same in a couple of minutes. If you don't have experience, maybe you require more time, but no more than 30 minutes and 1 hour. And that's all. So let's start the Q&A.
Thank you, Marcos, and good story. I like it, and I like the end of the story. Good to know that you have been spending a lot of time doing calculation, and you have experience on first person. I think we have some questions. So why you can read the chat. I wanted to let everybody that you can try Frenetic AI and Frenetic Magnetic Simulator for free. If you go to the link I've copied in the chat for everybody, so you can experience the whole workflow by ourselves. We have one question in the chat.
Yeah, I see. Well, two questions. That one, I think that you already solved it. Okay, which yeah, basically what I use right now is Frenetic Simulator. Okay, it's not the AI part. Frenetic Simulator at the end is our design software based on analytical and empirical equations. Okay, that's the reason why we can also run the simulations very fast. And the second one, which is maybe I don't understand. But it's can you simulate for bifilar winding done in 2 layers and 2 single filar windings connected in parallel. So let me show you the possibilities that we have here, okay? At least for the winding perspective, we are in an inductor, okay? If with transformer, there are more combinations, and also you can combine or twist, for example, secondaries and these kind of things. And here, what you can do is to, a part of simulate the leads wire, you can simulate also round wire, foil and rectangular wire, okay? And for example, with the round wire, you can do kind of the same of leads wire. For example, putting 40 parallels with a smaller strand diameter, but probably it's not, it doesn't has the same porosity factor as the leads wire, which is compact. Okay, and for the leads wire, yes, you can simulate a different number of strands, strand diameters, and specified insulation layers. And this is good if you require, for example, isolation between the primary and the secondary, and between primary and the core. Okay. Does the simulator take magnetic displacement inside of the core into account? To be honest, Well, what we do here in the core tab, okay, for the calculations, we use the statement coefficients, the statement approach, but not the classic statement. Okay, we use the improved generalized statement equations. Okay, to take into account the nature of the waveforms. Okay, and regarding the displacements, I don't know if you are referring if, for example, we have or we can assume that the two halves of the core are not aligned properly. Okay, I saw in the past problems with this alignment, not in ferrite, maybe more in nanocrystalline or amorphous material. I don't know if this is the question, okay, because maybe I don't understand exactly what magnetic displacement means, okay? But basically here, what we take into account, and at least in the core calculations, are the statement coefficients, okay, and improved general statement. And for the winding, what we have is a model to calculate the skin and proximity effects that our CTO developed, okay, which is a 2D model. And for the we also considered in the fringing flux effect, okay, in this layer, okay. But we give a rough number, okay. We doesn't give like in FEM the current distribution. So probably if you map in this, okay, what you will see is that the current density is higher here, okay, because you are reducing the effective resistance, or you are increasing, sorry, the resistance that you have in this part due to the fringing effect, okay.
We have you have the response of
Yeah,
the
the magnetic
verification.
displacement caused by the eddy currents in the core material. Well, as I mentioned, what we calculate here in the core are basically the statement coefficients considering this effect, the current effects of the material. So yeah, this is what we consider right now in the tool.
Okay. We are running out of time, so Marcos, if you can share the last slide, only to let people know that next week, our next live webinar is going to be about pulse transformer design for RLC loads next Wednesday. So thank you everybody for connecting today, and yeah, we'll send you the recording and hope to see you next week. Thank you. Bye bye.
Thank you. Bye bye.